Hello and welcome to the instructional video for the surplus production model with time-varying parameters. What I'd like to do in this video is walk you through how to run and modify the program for your own use. There are two ways you can run this program. You can either do it in AD Model Builder, which is the code in which it was written, or you can run it from the command prompt if you aren't familiar with ADMB, and I'll show you both ways today. But to get started, I want to walk you through the different files that are required to run this model. What you want to do once you have the files downloaded off the web is open up that folder in which you've saved it in File Explorer, and then you'll see there are 7 files. At the first 2 are the required for the executable. So this is the program itself. It's been compiled. So SPMTV, the .exe, and CPP you shouldn't be touching unless you overwrite it if you modify the code and recompile it in ADMB. But if you're just running it straight up from the command prompt, you shouldn't have to touch those 2 files. The next file I'll bring your attention to is the DAT file or .dat file, and this is where your data are. The second file that's important is the .tpl file. This is the actual underlying code, which you can look at in any sort of text editor or in ADMB itself. And if you want to modify it, this is the file you'll need to look at. You'll also need to look at the .cxx file if you want to modify the code, depending on what you're doing. That's the file that will allow the results from the model to be translated into an R object so that you can open it up in R, this R viewer code that I've provided, or whatever R code you want to write yourself, and view the output graphs. And then if you do want to use the R viewer, you'll need to make sure that this ADMB to R file is in the same folder. So without further ado, let's take a look at the DAT file, and I'll walk you through that first because the data is the first step, right? So at the top, you'll notice we have some information about the code itself and some warnings. So the first thing to note throughout is that missing years of data are indicated in this file with a -99. So if for some reason you have data in here that is the true value is -99, you'll need to rescale. And I would imagine that would only be in your indices, and I'm not sure why, but if you do, just be warned that you would need to change those values somehow. The next thing to note throughout is that any line with a # is a commented out line. So this is just the model ignores it. But it's important for you to, and you can add your own if you'd like, notes from me to you or for you to yourself. So for instance, these top 4 lines are not read in by the model, they're just notes to the users. So let's jump into the data. The first line that the model reads is the start year of the model, and the second line that it reads is the end year of the model. And this is really important for setting up the whole matrix of the data inputs that are read into the code. So the next important input in any surplus production model, of course, are the landings. And there should be one value here for every year between the start year and the end year of the model. And if you don't have that, you'll end up with an error message. So make sure that you have the right number of years of landings as you do have specified above here as your start and end year for the model. The next section are your indices of abundance. Now you can have in this program, you have to have a minimum of 1, but you can have a maximum of 4 indices of abundance. And note again, I'm warning you that if you have index values that are missing, so a given year where you don't have a value for that index, that's just perfectly fine, but you have to leave a placeholder, a -99, in that year because the model is expecting there to be the complete number of years of data points to read in, and then it will just ignore those points later on when it goes to use that data in the actual modeling process. So here, this is my first index for this example data set. So we have values from 1964 to 2012, and then the last 4 years from 2013, 14, 15, and 16, we don't have values. This index wasn't updated, and so we have placed in here negative 99s as our placeholders. So that's a good example of how you could do that. The second index that we have in this example is our an index that doesn't have values at the very beginning of the time series and only comes in I think this was 1980 through the end of the time series. Our third index here doesn't come in until 1990, and so you can see there's a lot of negative 99s until we get up to here, and then we've got data through the end of the time series. And then for this particular example, which I should have mentioned before, is Atlantic Menhaden, we don't have a fourth index, and so we have an entire time series here of negative 99s just to indicate to the model, ignore that slot for the fourth index. So moving on, the next section are the parameter values and starting values and priors. So a couple things to note here. This is set up so that you can have up to 4 indices, but as I'll mention later, you need to make sure that you're very careful about how you set the values for the phase and the priors in this section so that you get what you're actually trying to achieve. So let's walk through each one. So the first parameter is the intrinsic population growth rate, or R. The first slot here is the initial guess, or your starting value. We have a lower bound set and an upper bound, and we're telling AD Model Builder to estimate this parameter in the first phase, or the first go around in the likelihood estimation process. There are slots here that are filled for the mean of a prior and the log scale standard deviation of a prior, but as you notice here, the value I've selected for the prior PDF is 1, and if you look above here, we've said that a value in this slot equal to 1 means there's no prior placed on this parameter, it's only bounded. And if you set that value equal to 2, you're assuming a log normal prior. So in this case, for this particular parameter, we have placeholder values here for the prior, mean, and log scale standard deviation. That's just placeholders because we've said here there's no prior to be specified, so it just skips over it and ignores it. But as you'll see later on, we have a good example here. Let's move ahead. The carrying capacity is similar, such that we have an initial guess, lower and upper bounds, phase equal to 1, and then the prior is equal to 1, therefore no prior is assumed, and these are just these two values for the mean and the standard dev of the prior are just ignored. Here's a good example though where we have assumed a prior for our initial biomass. So we have our starting value for initial biomass, lower and upper bounds. We're estimating it in the first phase. And then we've set the prior PDF equal to 2, which means it's a log normal prior. And therefore, it's going to read in and use this information, so the mean of that prior and the log scale standard deviation. Then for each of our index values, we have to do the same. So you can see for our first index, we've set our initial guess, lower, upper bound, phase, and again, we're setting no priors for any of these parameters. So I'll skip down. We've got our first index, second index, third index, and then the fourth index. Again, we don't have a fourth index for this particular example, but we have to keep values in these slots as placeholders. So I just assume the same values as the last 3. But the two important things to note here. One is that if you don't have an index in a given slot, make sure that you set that phase to -1 to tell AD Model Builder to ignore that slot, essentially, that index, because you don't have any values there. And then make sure that you set the prior equal to 1, meaning that there's no prior, just to make sure there's no confusion in as the model is run. So I've left little reminders here for you that inputs entered for empty slots serve as a placeholder, and make sure that you set the prior PDF equal to 1, indicating that there's no prior if you're not using that slot, or if you have no index for that particular index slot. So moving on, the next set of inputs are the log scale standard deviations assumed for each survey. So again, if you don't have an index, you would use -99 as your placeholder. So here we have three indices. The first one we're assuming a standard dev of 0.25, the second index of 0.62, the third index 0.72, and then we have a negative 99 for our last parameter. And then you can see here I've commented out this second line. This is where, for instance, if we wanted to try a different set of values for that, or if you were iteratively reweighting this as you went along with multiple runs, you could have stored the previous values that you assumed for these standard devs for each survey. You just want to comment them out as you go along. Moving along to the next parameter, this is where you set up your time varying parameter switches and the phase in which you want those time varying parameters to be estimated. So you have two options with this code. You can either estimate time varying intrinsic growth rate, or you can estimate time varying carrying capacity. You can't estimate both. I've set it up so that you aren't allowed to with this code. If you think for some reason you have a very special case where your data are so super informative that you do both, let me know. And if you can convince me, I'll change the code, or you can do it yourself. But the default is that you have to pick one or the other. So in this example, we're assuming time varying intrinsic growth rate. And we're doing that by setting this value equal to 2. So if we had set it to a negative value, then the random walk is turned off and you're estimating one value for that parameter r. If it's greater than 0, the RDevs for each year are estimated and the phase is set to the number that you insert in this slot. I recommend 2 for annual deviations. You could use 1 if you wanted to. That's something you can play around with yourself. Whatever you do, don't use 0. That just confuses the model. So you want this to be positive if this is a time varying parameter, and you want it to set it to the value of the phase that you want ADA Model Builder to estimate those parameters in. So if you wanted to not estimate time varying r, but instead estimate time varying k, you would set this to a negative value and make time varying k a positive value, either 2 or 1 or 3 or whatever phase you want the model to estimate that those parameters in. So I'll just change it back. And then this next slot is for the standard dev of those annual deviations in either r or k. We have it set to 0.1 here. That's probably a reasonable value. If you set it to a larger standard deviation, the model is going to could have large spikes from year to year, chasing after each of the annual changes that it observes in the data. If you have it much smaller, you'll essentially be setting that to that parameter to not very time varying. So there's kind of a sweet spot in there that we've found in general is around 0.1, but that's something you probably want to play with your model and do some sensitivity runs. And then the last two slots here you pretty much want to ignore and leave alone. This is a penalty to make sure that the model doesn't move into a parameter space where the biomass runs to a negative number. And then this is the end check, which we'll show you in a moment. If your model reads, if you have set up your DAT file correctly and you are able to read in your data properly, this will the model will spit out 1, 2, 3, 4 just to check that and confirm that you have read in your data properly. If you've got a weird extra value or a missing value in your time series, this will not, you'll get an error message and you'll not see 1, 2, 3, 4. So that's something to look for. So let's look at the actual code itself. That's in the TPL file. This is the file that you, if you decide that you want to modify any of the code, you would need to dig around in here and do that yourself, and then recompile in AD Model Builder. And then also keep in mind, if you do that, if you change any of the values that you want to spit out into R for viewing the results, you'll need to probably or possibly change this .cxx file as well. So keep that in mind. And I think that's all we need to look at in our text editor. And again, I should have said at the beginning, you can modify these files, the DAT file, in any text editor, a basic text editor. I don't recommend Word or anything, or any word processing program, but you can do it in, I have Notepad or WordPad, but or you can open it up in AD Model Builder and do your modifications in there as well. In fact, let me do that next. So let's just open up, if you happen to have AD Model Builder loaded, which I should point here, I'll open it up and then I'll show you. This is the website for the AD Model Builder project, where you can get your downloads and get a copy of the program. Again, you don't need AD Model Builder to run this model with your data, assuming you don't want to make any changes to the code. But if you are an ADMB user, it's nice to have that functionality. So let's just go back to AD Model Builder. You would hit Open and then navigate to where the files that you downloaded from the website are located. You can open up the DAT file, and it looks a little different in here, but again, you can see all the data are laid out just as we went through the DAT file in the text editor. And then you'll want to open up the TPL file and go to the ADMB drop-down menu. And this it's already compiled here. If you wanted to compile it, you'd have to do the translate compile link or just hit the build option, which if you're familiar with ADMB, that should be no problem. If you just want to run it, you like the code as it is, just hit run, and there, it's already finished. If there are any you can scroll through this output yourself if you want to see how AD Model Builder went through the parameter estimation process. You can scroll through all this output and also confirm that it did indeed invert the Hessian and it finished in a proper fashion. So there's another option for running this program if you don't have or can't obtain AD Model Builder or aren't familiar or comfortable with using it. Once you have your DAT file all set up with your data, you go to either your drop-down window in Windows, or you can just type, if you have Windows 10, command prompt, and open up what looks like an old DOS screen. And then you need to navigate with the CD command to wherever your folder is that you stored the DAT and TPL file and the executable file. So in my case, it's an SPMTV video. And if I hit dir for directory, we can see that there's our SPMTV executable, the CPP file, and all the other files that we might need to run this project. So once you if you want to do it in the command prompt, make sure you have your DAT file all set up with your data, or you can run this example, as I'm going to do next. And then simply type SP, if I can type, SPMTV, and it runs the model the same as it did in AD Model Builder. So you can see it inverted the Hessian, and it shows all of your gradients through each of the phases that it went through as you scroll up and down. So let's see here, let's get to the end. So now it's run the model via the command prompt. So again, you don't need AD Model Builder if you're not going to change the code. You just need to change the data file to include your data, and then simply run it with this SPMTV command once you've navigated to the appropriate folder where all your files are stored. So once you have run the model either in AD Model Builder or in the command prompt, you will likely want to take a look at what your results are. And so I've created a very short but hopefully sweet R viewer for plotting up your results and giving a first look at how the model performed. So if you go back to your file folder that has all of the original 7 files plus all of the files that AD Model Builder creates, you'll find an rviewer.r file, which if you double click, it should open in RStudio or whatever R environment you like to work in. And then you'll need to make sure that you have two packages loaded. The first is Lattice, and the second is Fishgraph. Then make sure that your console is clean and you have no graphics open. And then you'll need to make a few modifications in this next section, the change this stuff section. So the first thing you need to make sure is that you have the working directory set to the location where your RDAT files are located. That's the file that the ADMB to R program creates from the TPL file from the AD Model Builder code using that .cxx file as a translator. So you want to set your working directory and then set your my working directory equal to the same thing with a / after it. So just run that, and then you'll read in your RDAT file, hopefully not get an error message. The next thing that you'll want to do is set up a list of names for each of your indices. So I had 3 indices. These are their names, PRFC, NAD, and SAD. If you had a 4th index, you just need to add a 4th name. Here we'll call it 4th. And if you have fewer than that, just delete those and add whatever names that you want to call your indices. The next option that you need to declare here or tackle is the option for whether or not you want reference points plotted on your biomass trends graphs. So I'm going to leave this equal to true, or plot B references or refs or reference points, because I want to show you all the options. But if you don't want that and you just want a straight up plot of the estimated biomass trend, change that equal to false or F. Then if you do want to have biomass reference points plotted on top of your biomass trend graphs, you need to specify what fraction of BMSY you want to plot as your reference point. And if you had already set this line above equal to false, you can just leave it as is. It will ignore this next line, no problem. But here I'm saying I want BMSY, or half of BMSY, to be my reference point for the overfish threshold. And then the next 2 lines have to do with your exploitation rate reference point, or U reference point. So this is your overfishing threshold. So if you want those plotted on top of your exploitation rate estimate graphs, you just set this equal to true. If you don't, set it equal to false or F. And then you need to define what fraction. So if you want it to be equal to MSY, set this equal to 1. I've set it equal to 0.75, or 75% of UMSY, and that would be my overfishing threshold. So those are the things you need to set up right away. The next set of lines tell you whether you want to, or give you options for whether you want to view your output in your R viewer screen here in RStudio, or whether you just want to output it as a PDF. So I'm going to choose to output all this as a PDF because I think it'll be easier to do or show you in this video. So, but if you don't want that, you just need to comment this out and run the rest of the code. But because I'm going to do this, I'm going to keep it as is and just grab all the rest of the code and run it. And then we will go back to our file folder where all of our output is stored. And if we sort by date modified, there should be a results.pdf, which, let me go back to R. If you scroll up to that PDF code line, line 31, you can change the name right there. If you want to call it My Results or Model 1 Results or whatever you want to call it, you just change this, this word results to whatever the name of this PDF file you want it to be. So let's go back to the PDF file. And the first graph that it outputs are, or the first set of graphs are actually from Fishgraph. They're standard output graphs from that program. You can read more about it in its help manual. But the first graph that it shows is a kind of a diagnostics plot that I really like, that the Noah Beaufort lab crowd ginned up. And it's a nice little viewer that tells you whether or not your parameter values for your model, whether the final estimate, where it is relative to your bounds and where it was located relative to your initial guess. So for instance, our R parameter, intrinsic growth rate, our initial estimate, if you recall, was 0.4. The final estimate was a little bit higher than that, this blue line. The initial guess is the orange line. And our bounds are in red. So it's far away from the bounds, which is good. That's what you want to see. And it's a little bit away from the estimate. Now our K parameter for carrying capacity, the final estimate is a bit lower than our initial guess, but it's nowhere near the bounds, and so that's good. You don't want to see any of your blue lines next to your red lines, either here or here. That means you've got some estimation problems, and you need to go back to the drawing board and look at all of your starting values and your bounds as to whether they're reasonable or not. B init also is the estimates approaching the lower bound but not near it. Recall that this had a prior on it. I'll show you in a moment the results from that. And then our index catchability parameter estimates are these next three. You'll notice on the right here that if you get a message no bounding issues in green, that means you're good, you're in the good zone. And if, for instance, with index 4, recall I didn't have an index. And so Fishgraph reads this in as a fixed parameter, but that's just because this is an empty slot. So you can ignore this last line. And if you only had one index, you would have this purple fixed parameter message for the last three rows here. So hopefully that's useful to you. And then these are some more diagnostic plots. In particular, if you used priors, these are really helpful. So these are your likelihood plots for each of your estimated parameters. You've got R and K here on top. Again, you can see the blue estimate and the initial guess in orange with our bounds in red. It's just a bounded parameter. There's no prior on it, so you see a flat line, uniform as your prior. Again, for K. Here, B init, here's an example where we had a long normal prior on this parameter. So you can see the prior in the black line, our initial guess for the mean of that prior in orange, and the final estimate for the parameter in blue. So you can see, even though there was a prior placed on this parameter, it moved away from the initial guess more towards a slightly lower value. And then our index catchabilities, index 1, 2, 3, and then 4, of course, it notes that it's a fixed parameter. That's just because we didn't have any data in that slot, so you can ignore it. The next graph that's generated is your observed and predicted index values. So in our case, we had 3 indices. The observed values are plotted with gray dots, and the predicted model estimates are the black line. So you can see we've got the one longer time series that ends in 2011 and our 2 shorter time series with the fitted values here. The next plot shows you the standardized residuals for each of those indices, so you can examine your residual patterns. The next plot is your estimated trend or value for the intrinsic growth rate or carrying capacity, depending on which time-varying parameter you chose. So this graph, if you had turned off the time-varying parameter switch and simply estimated one value for the intrinsic growth rate, it would have a horizontal line at that value for the parameter estimate. Instead, for this example, I ran it with the switch equal to 2. So it estimated time varying R in the second phase, and so we get time varying or annually varying estimates for R, and that's the plot generated here. The next plot is your estimated biomass, and because I selected the option for plotting reference points, it's also plotting our 50% of BMSY threshold as well. So here we have our time varying our time series estimates of biomass from the model, and our 50% BMSY line with the dashed red line. The next plot is our estimated trend in exploitation rate in black, with our specified reference point for overfishing of 75% of UMSY, which should look a lot like the trend in R, not surprisingly. And that's your red dashed line. Again, if you had turned off your plot ref options, you wouldn't see these red lines. It would just be the model estimates for biomass and exploitation rate. And then the final graph produced is your plot of surplus production. One last thing to note, that this model can be run in a Bayesian framework. In order to do so, that would be a very long video. It takes a while to run that whole process. But if you open up the instructions file associated, or you can find on our website right next to where you downloaded the code, there are step-by-step written instructions for how to do what I just showed you in the video, as well as details on the software requirements, implementation of the Atlantic Menhaden example, both in ADMB IDE and in the command prompt. And then if you scroll down to point number 6, it'll walk you through exactly how to run the Bayesian diagnostics on your own. If you have any questions or run into any problems with this code, please contact me or Mike Wilberg at Chesapeake Biological Lab, and we'd be happy to help you. And I hope that you found this instructional video helpful and that this model is useful in your research. Thank you.